start our review on enzymes and the macromolecules in general. So we're going to start with activation energy. So first of all, what is energy? It's simply the ability to do work. There are lots of different types of energy, but generally we agree on these 5 types of energy. What we are going to be concerned with down here is the chemical energy. So radiant energy, chemical energy, and a little bit of the electrical energy is what we'll talk about throughout our unit on cells. Chemical energy is the energy that's stored in the bonds of chemicals, such as sugar, and this chemical energy is transferred into other types of energy, such as thermal energy, or mechanical energy, or electrical energy. And radiant energy is simply light energy. When we talk about photosynthesis, we'll talk about how sunlight is processed into chemical energy. So those are the 5 basic types. Let's see. How are the states of matter related to energy? We know that in the states of matter, gas, liquid, solid, and plasma, you have varying amounts of energy. We're gonna skip that. So let's go into some chemical reaction basics, which you will need when we get to photosynthesis and cellular respiration. When you change one or more substances into one or more different substances, and chemical reactions always involve energy. It can be released, it can be absorbed. Sometimes you have the amount released and the amount absorbed is the same, so there's really no change in energy. Sometimes extra energy can be released. Sometimes extra energy is needed for the reaction, but energy is always involved. So here's what a basic chemical reaction would look like if you were to write it out in shorthand. And by shorthand, I mean using the symbols from the periodic table, so H for hydrogen, O for oxygen. On the left side of the equation, you always have your reactants, and on the right side of the equation, you always have your products. These numbers in front of the chemical symbols are called coefficients, and just like in algebra, this too applies to our H2 here. So we actually end up with 2 H2 molecules for a grand total of 4 hydrogens. So that's what the coefficients are. In this case, energy is needed to combine the hydrogens and oxygens to create water, H2O. Activation energy is the amount of energy that's needed to start a reaction. So the amount of activation energy needed varies from reaction to reaction. So in living systems, with all the hundreds of thousands of chemical reactions going on, that would be a lot of energy. Nature's answer to this are catalysts. And a catalyst is a chemical substance that reduces the activation energy needed for a reaction. Catalysts are specific to different types of reactions. There are many things in nature that can work as a catalyst. Elements can be used as catalysts, so nickel in its pure form is used to turn vegetable oil into margarine. That does not mean that there is nickel in margarine. It just means that it's the catalyst. It's the thing that enables us to turn vegetable oil into margarine. An example, catalytic converters act as a catalyst to transform poisonous gases into less harmful gases in motors. Enzymes is the group that we're going to be focused on. These other two are used in industry, and this one is our body's answer to a catalyst, and they're called enzymes. And it's a protein. Sometimes it can be an RNA molecule, and it's a catalyst in living things. So this is what we're going to focus on. So talking about energy. Here's our reaction. We're going to get A plus B, and we're going to make AB here. And this is time, so we're going from start to finish. And this is our energy. Energy that is used and energy that is released. So our red line is the reaction without an enzyme. So here comes our reaction. Over time, we need to use lots and lots of energy, and then some energy is released. So you're comparing this amount of energy used with this amount of energy that's released. And so if you were to calculate this, there would be a net loss of energy. So this reaction, putting A and B together, would require energy on the part of the organism. Now, if the organism has an enzyme, we get the blue line. So in the blue line, it requires this amount of energy, so far less than without the enzyme. So we've used this much, and this much ends up, this much ends up being released. So in the end, there's a net gain of energy using a catalyst. And that's it for activation energy.